So we're going to talk about the polarity of molecules, and it's all based on this electronegativity. So the first thing we need to do is know the shape, which we've talked about a little bit. No problem now. By the way, I made this long ago when this movie first came out, and the bond polarity. And the question here is, are there polar bonds? So the unequal sharing of electrons, that's what a polar bond is. So for example, if we have HH and HCl, right? Hydrogen bonded to another hydrogen, they have the same electronegativity, right? So they're like holding hands, skipping down the road, happy as can be. They are sharing their electrons exactly equally. But if you look at chlorine, chlorine is more electronegative, right? So if we go to our electronegativity, remember fluorine, sorry, I just dropped it. Fluorine is the most electronegative atom. So it's going to be pulling all of the electrons towards it. So whoever's closer to fluorine is pulling harder. Remember who's closer to francium, they're getting their electrons pulled away from them. So when we look at our periodic table, we know that chlorine is closer to fluorine. And so if we have our hydrogen, it is sharing exactly equally because they have the same electronegativity. But our chlorine and our hydrogen are not sharing equally, not at all, right? Because remember, this chlorine is saying, give me your electrons, give me your electron, give me your electrons. And it leaves this hydrogen a little bit negative, and it leaves the chlorine a little bit negative and the hydrogen a little bit positive. And this is what polarity is. So when we have unlike atoms, which means atoms that aren't the same, it has an unequal sharing of electrons, and the electrons will spend more time near the more electronegative atom. Chlorine is the more electronegative atom, which means the electrons are going to hang around here, making chlorine very happy and hydrogen very sad. And this is what we call a dipole. So this dipole is just so we can show who's negative and who's positive. So we have an arrow, and the arrow always points to who's ever negative. So whoever's more electronegative, that's where the arrow points. Whoever's on the other side of that one, the positive one, we just put a little like plus at the end of the arrow. So it always points in the negative direction. Okay, so this is easy. Polarity is easy for diatomic molecules, but what about the polarity if you have more than two atoms? So this is a little slide that's going to make your lives a little easier. So how do we figure out the polarity of molecules? So a non-polar molecule, homonuclear diatomic, that means same atom. That's like HH, right? Symmetric molecules do not have lone pairs. So it's either HH, same atom, or no lone pairs on the central atom, we'll talk about that, and only one type of atom bonded to it. And we're going to talk all about these. Polar molecules are heteronuclear diatomic, like HCl, different atoms. They have lone pairs on their central atom, or it's bonded to two or more types of atoms. Okay, so keep this slide handy because we're going to be using this for the next few minutes. Okay, so how polar molecules work is you have these two dipoles and you have a negative end and a positive end, and they are attracted to each other. So you have the negative end of one molecule attracted to the positive end of another molecule. That's what we have, we call these polar molecules, or a dipole attraction. Okay, so now let's see how the polarity influences things like melting points and boiling points. But before we do that, let's practice these Lewis structures. Okay, so let's just do, we already did NH3, so I'm just going to draw NH3 for you, because remember we did that yesterday. And we're not going to do BH2, that's an exception. So let's do CS2, H2S. Let's do those. And we'll do this one too. So CS2 for 6 times 2, right? So that's 16 valence electrons. Draw our skeleton structure. We've used 4, which means we have 12 left. We do lone pairs. 2, 4, 6, 8, 10, 12. Okay, well, we have 16. We can't add, we can't subtract. We're kind of stuck because carbon only has 4, right? So we're gonna make a double bond here. And I'm just gonna do the same one because I really like to make it pretty. Now we have our structure. Okay, so that's our CS2. I want you guys to try H2S and O3, and I'm going to give you like 3 minutes to try these two, and then we're going to do them together. But I really want you to try your own Lewis structures before I just draw them for you. So try H2S and O3, and then we're going to go over them in just a minute. Okay, so let's do H2S. So hydrogen, there's 1, its valence is 1. Sulfur, it's 8 total. So draw our skeleton structure as best as we can. We've used 4, means we have 4 left. Well, look, S. Here we go. Let's try O3. 6 times 3, 18. So O, 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 that's the only way you can really do this one, right? Minus 4, that's 14. 2, 4, 6, 8, 10, 12, 14. Remember, at this point, I have 18. I can't add, I can't subtract. All I can do is rearrange, which means I need to make a double bond. Make a double bond here. And there we are. There's our O3. Okay, now I'm going to do CH2Cl2 here so you can see. And I'm also going to do CH4. I'm going to make this up here. I'm also going to do CH4 right here. Okay, so that's 5, 1 times 2, plus 7 times 2, right? So when we finish this one, it looks like this. Just for time's sake, I'm just going to draw this one for you. Those are supposed to be 2 dots, by the way. And this is what CH4 looks like. Okay, so our goal is to figure out if these are polar or nonpolar. Okay, so remember, if it's 1 atom or 2 atoms, well, all these are more than 2 atoms, so this doesn't apply. Okay, so if there's no lone pairs and they're all the same, it's nonpolar. Or if there are lone pairs on the central atom or they're not the same around it, it's polar. Okay, so if we look here at our NH3, perhaps put those on here. So what we're doing is we're looking at that central atom. The question is number 1, are there lone pairs on the central atom? There's a lone pair right here. This is a polar molecule. And you're going to see it's going to become important in just a second. Let's look at this one. Are there lone pairs on the central atom? No. And attached to the central atom is the same thing. The same atom is attached. So this is non-polar. All right, let's look at this one down here. Let's look at our O. Are there lone pairs on the central atom? Yep. Polar. Okay, let's go over at this one. Are there lone pairs on the central atom? Yes. Polar. Let's look at this one. Are there lone pairs on the central atom? No. The next question is, if your answer is no, the next question is, are they both the same? So when we looked up here at this molecule, no lone pairs on the central atom, and our next question was, are they both the same? Yes. Here, when we go back down to this one, no lone pairs on the central atom, but are all of these around it the same? No. So this is polar. Now let's look at this one to see the difference. Again, no lone pairs on the central atom, but these around it are all the same. So therefore this is non-polar. By the way, this skill right here will serve you so well in 219 and 210, you have no idea. So I'm teaching you the shortcut way to figure this out to make your lives easier. Okay, so now, why do we even care if they're polar or not? So this is like the why. So first element and the formula goes in the middle. Oh, that's a great question. So how we did this, we tried to make it as symmetrical as possible. So someone asks, is it the first element that goes in the middle? Not necessarily. You want to make it as symmetrical as possible, but just as a guide, for example, like carbon does always go in the middle no matter what. But for example, like this one, the sulfur went in the middle because as symmetrical as we could draw it would be an S with 2 H's on the side. So you're trying to make it symmetrical. But in the case of carbon, you're just going to need to remember that carbon always goes in the middle. Always goes in the middle. Okay, so now let's look at why we care about this. Okay, so what we're going to talk about and what we've kind of been alluding to this entire time is first we learned about why molecules lose or gain electrons, right? Because they're trying to get to those noble gas configurations, right? They're all trying to get to 8 on the outside, that octet rule. But the question is, why do we even care? Like, how does that make any difference? Well, the reason like why water is a liquid is because of this. It's because of this polarity or these dipole forces. That's why, if anybody's ever seen a snowflake, the reason why this happens is because of what we just talked about, the polar or non-polar. So like this happens because of it. Look at these, right? This is all, everything we just learned can be, we can explain all of this. Could you imagine that? That's crazy. It's all very, very, very sad. Look at this. This is the car. That's an antenna. Can you imagine? How would you get into your car after that? Right? That would be crazy. Okay, so anyway, how do we explain this? Like, why is water a liquid? Why is water a liquid? Why are something gases at the room temperature? Why is oxygen a gas? Why is nitrogen a gas? Like, why is that? That's what we're going to try and figure out now. So when we add energy to liquids, what we're doing is we're pulling them apart. Same thing when we add energy to solids. What we're doing to add, when we go from a solid to a liquid, we're pulling the molecules apart. So the question is, what's holding these molecules together? And then what happens when we pull them apart? Melting is just pulling molecules apart. Boiling is just pulling more molecules apart. Oh, there goes my computer again. So there's 2 types of intermolecular forces. And intermolecular forces are the things that hold molecules together. The first one is dipole forces. The second one is London forces. So we have dipole and London forces. So dipole forces is exactly what we just talked about. When you have a polar molecule attracted to the other side of another polar molecule. That's what we call a dipole force, because it's one dipole attracted to another dipole. So let's look at HCl, which we just talked about, right? So we were just talking about HCl. So if you have 2 HCl molecules, right? Chlorine, right, is a little bit negative, right? Because it's trying to steal all the electrons, right, and keep them around chlorine. Hydrogen's a little bit positive. When you put one HCl molecule next to another HCl molecule, they attract to each other. And this is what a dipole-dipole attraction is. The stronger that attraction is, the harder they are to pull apart. Now, super, super, super strong dipole, which is still dipole, is called hydrogen bonding, which isn't actually a bond, but we call it hydrogen bonding. It's a very poor name. It's just a super strong dipole-dipole. And this happens with hydrogen and a really electronegative atom like oxygen or fluorine, something of that sort. So hydrogen bonding is just really strong dipole-dipole. So just remember that. They're the same thing. This one's just extra, extra strong. Okay, so now, which one is more polar, HCl or HBr? So if we look at this, so we have HCl. Here's the Lewis structure for HCl. Here's the Lewis structure for HBr. Which one do you think is more polar? And how could you tell? Right? I'm seeing a lot of them. Yeah, it is.
Is it HCl?
Yeah, it is HCl, because when you look at your periodic table, the Cl is closer to fluorine, right? And since Cl is closer to fluorine, that means it's going to be more electronegative, which is going to make this right here more negative than this. And so HCl will be more polar. Now, after that question, which one's going to have the stronger dipole-dipole forces, HCl or HBr? So remember, dipole-dipole force means when HCl is attracted to another HCl, or when HBr is attracted to another HBr. Which one's going to be stronger? Yeah, HCl. Because again, the reason it's stronger is because this is more negative and this is more positive. So the attraction between them is stronger. This is less negative and this is less positive. So this is going to be a stronger attraction. So now here's the whole thing for the whole semester that we've been getting to. Which one of these, so I'm going to ignore this one right here. Which one of these is going to be harder to pull apart based on what we've talked about right now? Do you think it's going to be harder to pull apart the HCl or the HBr? Yeah, it should be harder to pull apart the HCl. Yes, and the reason is because it's a stronger attraction. So now I'm going to draw this one for you. So this is water. And I'll draw this again. I'll have this in picture in just a second. Okay, 2 water molecules. And so when we do this, you can see water is more electronegative. So water's a little bit negative. Hydrogen's a little bit positive. Hydrogen's a little bit positive. Water's a little bit negative. Hydrogen's a little bit positive. Hydrogen's a little bit positive. This here is that intermolecular force. But if I draw another water molecule, those are supposed to be lone pairs. Look what this water molecule just did. It just made a dipole in 2 places. So it made a dipole there and one here. So it's like a double dipole. It's like an extra strong. So water's incredibly strong, very, very hard to pull apart because it can dipole bond or have dipole force in 2 places. So water's boiling point is higher than the other boiling points because it's harder to take apart. So therefore, the stronger the attraction is, the harder something is to take apart. The weaker attraction, the easier it is to take apart. So if we let's look at oxygen. Here's oxygen here, right? That's our Lewis structure for oxygen. So this would be a non-polar molecule. And why is this non-polar? Because it's 2 atoms and they're the same, so it's non-polar. Same thing for nitrogen, which we've done nitrogen a couple times also. This is also non-polar. So therefore, what holds one oxygen molecule to another oxygen molecule? Not a dipole force, right? It's not very attracted to each other. So therefore, same thing with nitrogen. These are both gases because there's nothing really strong holding them together, where water is a liquid because we have this positive and negative force holding them together. And now again, why do we have this structure of water? Let's go back all the way back to what we talked about yesterday. This structure of water was so hydrogen can get to 2 valence electrons, so oxygen get to 8 valence electrons, right? Which was all based on where the electrons were located in oxygen, because remember, oxygen needed to gain 2 to be like a noble gas. Because of that, we have these lone pairs in our Lewis structure here. Because of those lone pairs, and this electronegativity difference, that's why we have these intermolecular forces. So it goes all the way back to where we learned about electrons to why molecules behave the way they do. So now, ignore this. So we're gonna look at hydrogen bonding just for a second here. So hydrogen bonding, like I said, is just super, super strong. It's a dipole force, but it's just very, very strong. But it's not an actual bond, it's just an intermolecular force. So when we look at this, hydrogen bonding is between an H and either an H and N, an H and O, or an H and F. Okay, So you can remember this because hydrogen bonding is FON. Get it? FON. Or as some of my students say, that hydrogen bonding is NOF fun, right? So that's how you can remember hydrogen bonding. So hydrogen bonding is either between an HF and HO or a HN. It has to be directly attached like this for hydrogen bonding. So you can remember it's NOF fun. That's how you can remember this. Okay. So let's look again. Here's a much, I knew I had this picture. Here's a much better picture of water, right? So we have all these, again, these are little dipoles that are pointing towards the negative with the plus toward the positive. And you can see they have these dipole forces in more than one place. And so you can see these are the attraction. So again, this is just dipole, just because it's because it's really, really strong, we call it hydrogen bonding. But it's just super strong dipole. It's the same thing. So these dipoles are what hold together things in solids and in liquids, right? That's what keeps, like, water ice. This is what water ice looks like. If you've ever noticed, have you ever put a water bottle in the freezer and you're like, oh, I'm just gonna get it cold real fast, or a soda can or a soda bottle, and you put it in the freezer, like, I'm not gonna forget it. I'm not going to forget it at all, right? And then you forget it, right? And then it's like all over your freezer, right? It's very bad. The reason that occurs is because the way the water molecules line up when they freeze, they make these really cool honeycomb structures. So, like honeycomb cereal, if you've ever seen it. And so water actually expands as it freezes because it's trying to maximize these attractions right here. And in doing that, it makes these cool shapes, which has this space in the middle. So when water freezes, like when water's a liquid, they're all just mixed together. But it freezes, it makes these really cool shapes. This is also why snowflakes look so cool. Okay, so now you can explain why everything blows up in the freezer, right? So another place you've seen these hydrogen bonds, by the way, biology, DNA molecules, right? What holds the double strands of the DNA molecules together? Hydrogen bonds, right? If there was no hydrogen bonds, there would be no life on Earth, right? If we didn't have these hydrogen bonds, that's what's holding our DNA molecules together, which you probably learned that in biology. You probably just didn't understand why they were there. Okay, so now let's look at these, and I'm going to draw these for you so you can see. By the way, when you take 219 or 210, anybody who's taking 219 or 210 or any kind of chemistry and nursing, you're going to be drawing so many Lewis structures. But I'm going to draw these for you because these take a little while. I would never, by the way, expect you to draw anything. I would expect you to be able to draw that one and that one. At this point, I wouldn't be able to expect you to draw the others. So here's what they look like. By the way, if you've ever wondered what organic chemistry is, it's just drawing a lot of Lewis structures. Okay, does the first one have hydrogen bonding? What I just drew, just number one, does it have hydrogen bonding?
Yeah, because the N, right?
Yep, this right here. That's that hydrogen bonding. And so it can hydrogen bond to another molecule. Okay, I'm going to draw an F3. Does this one have hydrogen bonding? Does number two have hydrogen bonding?
No.
No H's, right? So you can be like, I don't need, that definitely doesn't have hydrogen bonding. Okay, let's do number three. Here's number three. Does this one have hydrogen bonding? This one's a little trickier, right? It has O's and it has H's, but it's the O next to the H. Yeah, no, it does not have hydrogen bonding, right? Because remember, it has to be next to it. It has to be attached. The N here was attached to the H. Even though this does indeed have H's and O's, they are not attached to each other. The H's are attached to the C's. Okay, so I'm just going to erase this one so I can draw the next one. Here's this one. Again, don't worry about drawing these Lewis structures. I just want you to identify it. I'm not going to ask you to draw anything that's crazy. Does number 4 have hydrogen bonding?
Sort of.
Does this one here have hydrogen bonding? I'm seeing a few yeses and a few nos. Yes. No.
There's an H connecting to the O.
Yep. There is. That's what you're looking for. That's the hydrogen bond right there. Okay, for number 5, I'm not even going to draw that Lewis structure because you already know the Lewis structure. But even if I didn't draw the Lewis structure, does number 5 have hydrogen bonding?
No.
Yeah, remember hydrogen bonding has to be between an F or an N. There's no F or an N in that one, so just no hydrogen bonding. Okay, so that is our hydrogen bonding, which again, when you are in 219 or 210, those of you going there, or any of you in nursing, you will do a lot of this. Okay, so we talked about dipole, and we talked about hydrogen bonding. But remember, hydrogen bonding, it's a dipole. It's just a super duper strong one. The other one we didn't talk about is London forces. So London forces are between non-polar molecules. And so we call them London dispersion forces. Sometimes we call them dispersion forces. Sometimes we call them London forces. We call them all sorts of things, or LDFs. So London dispersion forces are non-polar molecules. This means, and most of these molecules are gases like N2 and O2. The reason they're gases is because there's nothing strong holding them together. Remember, if something is really strong, if it's tightly held together, which means it's very strongly attracted to something else, then it's going to be a liquid or a solid. But if it's not strong, it's going to be London dispersion forces. So I love this picture. By looking at this picture explains London dispersion forces. Do you think those forces look strong or weak?
Incredibly strong. I don't doubt it.
Right, very strong, right? These are very, very super strong. No, very, very weak forces, right? So this is how I always think of London dispersion forces. We also call them induced dipole forces. Okay, so now this topic that I'm going to talk about right now, in 219 and 210, sometimes people get confused about it. That's why I want you to see this now. So we call these, again, London dispersion forces, or they're induced dipole forces. So we all can agree all molecules have electrons, right? We can agree this. Well, what if one molecule that has electrons gets close enough to another molecule that also has electrons, right? The electrons are going to repel each other. And when they do that, there's this tiny little attraction with the positives and negatives. Now, remember, this isn't actually positive. It just ends up being positive because all the electrons are on this side. They're like, get away from me. I don't want to be around other electrons. And because all the electrons left this side of the molecule, all of the electrons on this side of the molecule are like, oh, I see leftover positives. And there's this temporary, instantaneous, super tiny attraction. Because remember, electrons travel ridiculously fast. So this means that this tiny attraction lasts like picoseconds. It's there and it's gone. But then it happens again, and it happens again, and it happens again. And so it's a very weak attraction, but it happens over and over again. So these are very weak attractions, very, very weak attractions. And they're temporary, and they last just a second. And the more electrons a molecule has, which means the bigger the molecule is, the stronger the London dispersion forces are. So if it's a really big molecule, it has a lot of electrons. So which means there's a lot of pluses on this side, right? And then a lot of negatives on this side. If it's a little molecule, there's only a few pluses and a few minuses. So bigger molecule, stronger attraction. Okay. So now when we look at this, we can just look at the size of the molecule to figure out which one is the stronger of this two. So which one do you think is going to be stronger? So remember, stronger London dispersion forces, more electrons. A way that you can kind of just keep this in your brain, look at the molar masses. The heavier the molecule is, the more electrons the molecule has. So which one for number 1? Yeah, Kr. How about number 2? So I have the stronger for number 2.
HBr.
HBr, literally just because HBr, oh, I gave you the next one, HBr is bigger, so it's stronger. How about for number 3? Which one's bigger? I know I just gave you this one, right? Yeah, C2H6, because this one has 1 carbon, this has 2 carbons, 4 carbons, 6 hydrogens, right? The bigger it is, the stronger the attraction, or the stronger the London dispersion forces are going to be. So now, oops. Okay, when we look at this one, which one has a stronger London dispersion force, CH4 or SiH4? Yeah, SiH4. Okay, my next question. Which one has a higher boiling point, CH4 or SiH4? I'm looking up the boiling point of SiH4 after you decide what your answers are. Waiting for a few more answers here. Yes, SiH4. SiH4 is boiling point is negative 111. CH4 is negative 161. Now I'm going to take that CH4 and I'm just going to put a Cl here. This one is negative 24 degrees Celsius. So CH4 boiling point is negative 161. Why? It has very, very weak London dispersion forces. SiH4 has more electrons, so it has a higher boiling point, right? Now again, look at how low these boiling points are because they're only London dispersion forces. But this molecule, this is polar. Remember, so if it's polar, this side of the molecule is a little bit negative and this side of the molecule is a little bit positive. So it can be attracted to another molecule. This attraction.
Are those negatives or like dashes?
These are like dots.
No, I mean like
this.
Yeah.
Oh, this is a negative. This is a negative sign. Yeah, these are actual like negative 161, negative 111, and this is negative 24.
Okay.
So you're welcome. So when we made this polar, look at how much higher the boiling point was because now it's held together really, really, really closely, right? So I just looked these boiling points up, by the way, just so you can so you can see that this is real. You would never actually need to know the boiling points. You would just need to know who is higher or who's lower. So now look at this one here. Let's do water. What's water's boiling point? Just because I know you all know this.
100 Celsius.
Yeah, 100 Celsius. Look at the difference between these molecules, right? London dispersion, they're held together very weakly, right? And so this is a gas at room temperature. This is a gas at room temperature, right? And it boils all the way down here. And the reason it's a gas is because there's nothing really holding it together. This boils at -24. So it's probably a gas at room temperature also. This is a liquid at room temperature because of this hydrogen bonding, right? Because it's so strong. So we can use these to predict why molecules are liquids, why molecules are solids, and why molecules are gases. It's all because of what holds them together. And remember, how we got these Lewis structures in the first place was learning how to do like 1s2, 2s2, 2p6. We used that to get to this whole piece. Okay, so looking at that again, you can see here's your CH4, SiH4. See, the heavier they get, the higher the boiling point is. And we can look here is like our chlorine gas, bromine gas, iodine gas. They have higher boiling points. But again, the heavier it is, the more electrons there are, the stronger the London dispersion forces are. So let's just look at we're just going to look at some molecules just so you can see. So let's look at, here's your natural gas. That's like what comes out of our stoves. That's like CH4 to CH, you can't really see that either. So just so you can see what these hydrocarbons look like. So here's CH4. And here's like C4H10. Oops. It's just C's with a bunch of H's around them. And so just imagine looking all the way down there to that C23. It's just 23 hydrogens with, 23 carbons with hydrogens everywhere around it. That's all it is. So we look at this, natural gas, that's what we use to cook, right? Propane is 3 C's. Again, it's a gas we use to cook. Go all the way down here. Here's gasoline. Here's what you put in our car, right? So here, that's octane. It's a liquid, right? It's got more electrons. Octane has more electrons than methane. So therefore, its London dispersion forces are stronger, meaning it's harder to take it apart. So octane is a liquid at room temperature. But when you get gas, can you smell it? Right? That smell of gas, which is very bad for you. You should not smell gas. It's very dangerous. It's barely a liquid at room temperature, right? That's why we have to put the gas cap on the car, right? If you don't put the gas cap on the car, you know what happens? All the gas evaporates. Bye-bye gas. That's why we have the gas caps, because it's barely a liquid at room temperature. It's really, remember, it only has London dispersion forces, so it's easy to take it apart. So we got to put the cap on the car. Now, if you look at this, down here is like paraffin wax, right? These are actually going to be solids at room temperature because they're just so big. They're so big, so many electrons, they're like actually solids at room temperature. Okay, so we're gonna skip this one. Let's see here. Let's try this one. Let's just do number 1 here. And number 3. We're going to skip number 2. That's just another rule that we don't need to know right now. Okay. Which one of these 2 for number 1 do you think has the highest boiling point? Remember, highest boiling point means hardest to take apart. So who's the hardest to take apart here? CH3OH or CH3SH? I see a few. Yeah, I don't even need to draw these little structures now because you can kind of see it. So when you see the structure, what you should see is this. Oh, you're like, OH, that's a hydrogen bond. That's strong. So this is going to be a higher boiling point, right? Let's do number 3. Who do you think is going to have a higher boiling point, CO or N2? Remember, highest boiling point means hardest to take apart. Seeing a few. Yeah, CO, because this one's polar and this one's nonpolar. Now, if you're like, how did you know it was polar or nonpolar? Remember, if there are 2 atoms and they're different, it's polar. If there's 2 atoms and they are the same, it's nonpolar. Nonpolar is LDF, London dispersion forces, which are weak. Polar, strong. The stronger it is, the harder it is to pull apart. Okay. All right, so let's just review this really quick. So we have intermolecular forces, dipole-dipole, and hydrogen bonding, they go in together, and then London dispersion forces. Now, all of these are much, much, much weaker than ionic or covalent bonds, much weaker. So if we look at this, oops. So if we look at a water molecule, this little dots, those are intermolecular forces. So to split or to separate a water molecule, that's gonna, if we want to separate all the water molecules, that's like at 100 degrees Celsius to separate all of them, right? Do you know how you actually separate a bond from water? Does anybody ever know how to do that? Electricity, right? So you can boil water and you can separate the water molecules, but you have to run electricity through it to actually break a bond. To actually make these come apart, you have to use electricity. So ionic and covalent bonds are so much stronger than these intermolecular forces. The intermolecular forces are just holding one molecule to another molecule. Ionic and covalent bonds, these are much stronger. So our intermolecular forces are strongest as hydrogen, then just regular dipole-dipole, and then London. Remember, the stronger the intermolecular forces, the higher the boiling points or melting points. Okay, so again, the larger the attraction, the higher the boiling point, and the higher the melting point. I love this picture, it's art. Do you get it? Look, it's an ice cream truck, but it melted. Huh? Oh. Get it? It's a melted ice cream truck. It's kind of funny. That was a funny picture.
I want to die.
Okay, and this is also why polar molecules dissolve polar molecules. So this is why we call water the universal solvent, because anything polar will dissolve in water. This is why alcohol dissolves in water, right? And nonpolar molecules only dissolve nonpolar molecules. Think of like, has anybody ever had Italian salad dressing, right? You have the oil and the vinegar and they separate. Well, the oil is nonpolar and the vinegar is polar. They don't want to be near each other. They're not attracted to each other at all. You have to shake it up and then you get them to mix for a minute. Or if you remember when you used to go to restaurants, right? And you'd go to a restaurant and they give you olive oil and vinegar and you could dip your bread in it, right? Those days when you got to go to restaurants, right? The reason that the olive oil and vinegar don't mix is because the vinegar is polar and the oil is non-polar. So this whole polarity, this explains why molecules behave the way they do. Okay. All right, so that is our whole 209. You have finished 209. You're done. Yay, congratulations.